My name is Rumman Mahmood, and this is my report for Lab 3. For the purpose of this lab, we are trying to observe and obtain a better understanding of magnetic fields through visual representation to then observe the relationship between distance and magnetic field, and to explore Biot-Savart law. For the fundamentals, there is the previously mentioned Biot-Savart law, which relates the magnetic field at a point around a small piece of current. The distance dependence formula of a bar magnet is also used, and finally the bar magnet will be representing a magnetic dipole, so the equation for a magnetic dipole will be used. For the preview, it was determined that the magnitude of the magnetic field decreases as the distance from the magnet increases. N ended up being negative 2.805, while the magnetic dipole moment ended up being 3.64 ampere meters squared. For the models, system, and surroundings, the phone/magnetometer was the system, while the surroundings was the bar magnet and Earth. The bar magnet modeling the dipole itself was the main assumption of the lab. For the initial conditions of the lab, I just placed a bar magnet at one end of a meter stick that was oriented east to west. The details prior to the actual procedure included me locating my phone's magnetometer chip and then determining magnetic north. To determine the actual location of the magnetometer, this process was carried out starting with moving the phone perpendicular to the meter stick until the absolute value of the x component reached a maximum. Then that position was marked with tape. The phone was then rotated 90 degrees and moved perpendicular to the meter stick with another piece of tape being placed. The intersection of the tape was then determined to be the location. The experiment was then conducted. The phone was moved to various distances from the bar magnet to measure magnetic field magnitudes where the x component equaled the listed values. Then for measuring the off-axis field, the perpendicular distance where the net field equaled 100 microteslas was measured. The app was then used to find all components of the net magnetic field. Then the y component was adjusted to correct for Earth's magnetic field. This is the data for the whole experiment. The upper left section contains distance measurements for different magnetic fields. The right side shows a linearized plot of the averages. The bottom section shows the data for the off-axis portion where the magnetometer was moved up and perpendicular to the axis. Now, based off the data from earlier, n and k can be determined as n is the slope of the linearized plot, and the natural log of k is the y-intercept. Using these values, mu can be found, which is determined to be 3.64 ampere meters squared. Now for the coding section. First, the initial conditions were set and a function for the magnetic fields were set. Then the visual aspect was coded, where the magnitude and direction for 2 on-axis arrows, 4 perpendicular off-axis arrows, and 1 arrow that was 45 degrees from the axis were specified. For the model itself, purple was used for the on-axis arrows, blue for the perpendicular arrows, and red for the arrow at 45 degrees. The computed magnitude is then pasted. With that computed magnitude, we can look at discrepancies. As you can see, the 6.23 e to the negative 5 compared with the 6.63 e to the negative 6. The possible reasons from this lab for these discrepancies include inaccurate readings and angle and the possibility of other magnetic fields being present that weren't accounted for. Now for the discussion question. This one asks what would happen if the meter stick wasn't oriented to compensate for Earth's magnetic field, and the answer to this is that there would be an interference from Earth causing the x component to no longer be 0. The next question asks what would happen if 2 identical magnets were stuck together end to end. The answer to this is that the magnitude would increase while direction stays constant. Some conclusions from this experiment are that we determined that magnitude of magnetic field decreases with an increase in distance from the magnet, and we also learned how to use a magnetometer to determine magnetic field, in this case, magnetic field of a bar magnet.